This little video is just going to be on how to do the analysis for solving for specific heat capacity using the direct method that we did in class. So if you remember, we went over in class that we said we're always assuming that the heat gained by the block is equal to the heat loss or the heat given by the heater. And one of our big assumptions in this experiment was that there was no heat given to the surroundings. So completely the gain was equal to the loss or the supply. So in this case of the supply, we said that the electrical energy was the potential difference, the current and the time. And that was going to be equal to the Q gained, so the heat gained by the metal block, whether it was aluminium or copper, whichever one you were using. So that was the mass, the specific heat capacity, and then the change in temperature. So what we can do here is that we can equate both sides. So VIT equals MC delta T. Again, that big T representing temperature, little t representing the time passed. So if we rearrange this to kind of linearize the equation, we always want to have our dependent variable, which in this case was the temperature measured on our y-axis, and we want to have what our independent variable was, so in this case the time passing, on our x-axis. So if we just do a little bit of manipulation here, we can just say and take delta T and make that the subject. That's equal to V times I, so potential difference in current, divided by mass and the specific heat capacity. And so this becomes just a y equals mx equation. And again, you can have your temperature in degrees Celsius or Kelvin at the side, just your scale will be different, but it's exactly the same process for both of them. So looking at this, we can see y equals mx. So what it tells me is that my gradient, so the gradient of this graph, all right, must be equal to potential difference current divided by the mass and the specific heat capacity. Okay, so if I want to find the specific heat capacity, I'm just going to go to quickly insert an equation. So if I want to rearrange to find C is going to equal, all right, to make subject here, or let's just write out actually the gradient. The gradient is going to equal, the voltage, the current, mass, and specific heat capacity. And so if I wanted to, I can then say, okay, so C was going to equal, and if I place this up, C is going to equal V and I divided by the mass times the gradient. I'm being really careful here because I often use the symbol M for both mass and gradient, so I'm writing M and gradient, just so we can sort of can see the difference between the two of them. Again, you can put this in whole words. So that's how I'm going to rearrange to hopefully find the specific heat capacity. All right. So again, you need to have made sure you've measured that potential difference, you've measured that current, and you've measured that mass throughout. So if we take a little look at our graph here, all right, this is actually just this previous student's one that they used. Now, your graph may not be completely linear at the beginning. It might have taken some time for that heat, for the block to heat up. So you might have a little bit curving at the bottom, but we want to just be looking and analyzing the linear section. All right, so in this case, we're going to be looking at our gradient. So on Logger Pro, it always tells us the EM of the slope, and we've got that written here. We've also got our y-intercepts as well that can be shown. All right, so those are the two things that I might want to talk about. So in our graph analysis, we're going to discuss kind of what the graph shape is. Was it relevant to our hypothesis? What we said here is that temperature and time were directly proportional. So I want to talk about the relationship. Is it directly proportional? With that, I want to mention the idea of the shape. So discuss the type of the graph that we've got. Does it pass through the origin? Was it supposed to pass through the origin? Well, at 0 time, it's at room temperature. Should it have passed through the origin? That discussion also going in. And then we also then want to mention our slope. When I talk about the slope, it's about the gradient. How much does it increase each time? How can I use that gradient to comment on the specific heat capacity? So in this case, we're then going to show that calculation, all right, and we're going to calculate C in our graph analysis. So in this case, our VIT over M delta T, and again, VI over M times the gradient. At this point, I'm going to put in my known values, so my potential difference and my current. I'm going to put in the mass of my block, which we should have measured, and then I'm going to put in my gradient. Now up here, you could either just use the gradient directly, or if you've used a max and min line, you might want to put in an average gradient. Again, just depends on whether you've done max and min lines on yours. So at this point, if I can calculate and rearrange for my gradient, it gives me a specific heat capacity of 505.9. And again, I've used the equation function here just to keep it nice and neat. What I want to now do is compare that scientifically Okay, also kind of justify scientifically my results. So what I'm going to do is compare it to a known value for the specific capacity of steel. So in this case, I'm going to look this up. You need to have a little look, research it, find it out, have a citation in there. And then what we're going to do is the percentage discrepancy, or the percentage error, it's also called, where we're going to do the accepted value minus the experimental value divided by the accepted value. Again, taking the positive of this, timesing it by 100 and placing it into a percentage at the end. Now at this point, like 0.95% is not very clear. So what I'm actually going to do is go in, and so it's a little bit too precise for me. I don't mean not very clear. And in this case, usually we try and give integer values for our percentage error. If it's like 0.5 or 0.4, you could leave it at that, but this would just round up to 1%. If it's 1% percentage error, we could say that's pretty accurate, all right, or very accurate. So again, in your little graph analysis, I want to see a discussion of, have you answered your hypothesis, relate it to your graph shape, relate it specifically to yours, comment on some of those values. Okay, so relationship, origin, shape, and the slope. Use the slope to calculate your C value. And with your C value, compare it to a known one. That's then giving you your scientific comparison. And then give me your percentage discrepancy. It's also known sometimes as the percentage error. Oops. So you could also call it your percentage error. And again, giving that value here. If it's usually around about below 5%, we say it's very accurate. So that's kind of another little thing that you can do at the end there. Again, if you have any questions, please let me know.